Let's go. Hello, everyone. Welcome to today's brand new episode of Corecast. I am your host, Tim.
And I'm Mikey.
And this is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. Before we get started, if you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode, and we can get to that during the episode. And that's a bit redundant, I just said. So without further ado, let's get to it. I guess Tim, we were talking about about different, what would it be like to write on the back of like different particles, and we came across the notion of different candidates for unstoppable particles. We've been talking for the past few episodes about like particles and special particles, like the candidates for the quote unquote God's particle and also the keystone particle. But I guess now we can talk about like what's the most unstoppable particle in some sense. So,
Yeah.
Mikey, you seem eager. I'm gonna throw this off to you.
Just jump to Mikey.
Wait, what do you mean by writing on the back though? Like, does that mean that I take on the properties of that particle? Sorry, that's why I was so.
It's like it's like sitting in a car. Like you were like sitting on the particle and like on its back and going through.
Yeah.
Wait, but if I'm sitting on an unstoppable particle, I can still be stopped. So I would just get knocked off it, right?
I mean, clearly it's not the most well thought experiment, but.
All right, Tim, you go. Mikey's giving me a lot of flack.
I mean, this is kind of referring to.
Flack. I just thought of this conundrum, but yeah.
I mean, Einstein's thought experiment came to be because he was curious about the concept of space-time, and he wondered what it would be like to ride on a beam of light, basically. And back in the days, I guess if the question, what is the most unstoppable particle that exists, probably one of the prime suspect, the prime answer would just be the particle of light, the photon, right? Because it travels at the speed of light. And from Einstein's theory, when something travels at the speed of light, it actually cannot slow down ever. It will always be at the speed of light, and in that sense, it is unstoppable. Like it can never slow down. You can never catch up to it. So I guess
you can eat it.
What do you mean by eating it, Mikey?
You can absorb it. Well, it can become something else. Yeah.
Yeah, so I guess particles of light as it travels through, yes, indeed, it does travel at the speed of light, and you can't slow it down, but it does interact with other stuff. So to stop it or just destroy it, obliterate it, you can just grab an electron that has or multiple electron, just put it right in front of that photon, or you can tune the frequency and whatnot. And lo and behold, that electron will happily gobble up that particle of light, and there goes your unstoppable beam of light. So not quite
I have a perfectly spherical mirror, and I just bounce a beam of light.
You can also do that.
Wait, isn't that still like the spherical shape is made up of like things, right? Like it's made up of particles, like electrons and stuff. So you're still absorbing and then emitting.
Yeah, it's kind of hard to talk about like a specific photon, right? Like they have names or something. You can't really know if it's the same one or not.
Yeah, microscopically, it's like some particle of light is getting absorbed by the electrons in the mirror, and the electron jiggles and it emits, and it so happens so fast that it fools our eyes to some extent. But it makes no sense to talk about, is it the same photon? Is it a different photon? Because, as we have discussed in previous episode, all particles of light are identical. Absolutely identical in every way, except maybe their specific direction of traveling energy. So it doesn't really make sense to talk about the same or different. Huh? Yeah?
I heard that the LHC produced double photons. So can't I name that one? What's the deal there?
I mean, you can name them by their special by the attributes they currently have. Like, I think, Mikey, what you're referring to is the Higgs boson decay, the famous Higgs boson decaying into two particles of light, which ultimately led to their discovery. And of course, when they absorb in a detector, you can label them, be like, hey, dude, I see some particle of light in this part of the detector versus that part of the detector. So I guess we don't really label particles by their intrinsic attributes, but rather than like observational facts, then you can kind of name these particles. But it's only, but even then, it's not like exact, right?
No, that's
Yeah.
more like if you have like a swimming pool, right? You can splash it, and then a drop comes out, and you can name the drop, but pretty soon it's just gonna go back into the water.
Right. Once you go back to the pool, then yeah.
Yeah. So I guess I want to take a step back and ask like a question of even though a photon's not unstoppable because you just put an electron there and it gets absorbed, what would it be like to like I guess like be a photon? Like what would you see if you were a photon? Like if we're just speculating on this.
The whole universe would be a pancake.
What do you mean the whole
Yes.
universe would be a pancake?
I mean,
What is
there's actually a very nice analogy, not just like in terms of language, just saying this analogy, but mathematically. So there's one property of the photon is that when it travels the speed of light, and it means that nothing else can catch up to you, right? It turns out the math is very similar to, let's say, when you're falling into a black hole, right? When you're falling into a black hole, and the fact that and as you fall in, the fact that you cannot escape, even if you were to travel at the speed of light, also means that like things can't really catch up to you in that way, right?
Hmm.
So at the moment you fall through that event horizon, you're kind of things that are outside the event horizon. You kind of lose track of them because they're almost in a different universe now. Because if they fall in, they'll never be able to escape out. So, mathematically, if you look at the perspective of an observer that's moving faster and faster and approaching the speed of light, it's kind of like going into a black hole a little bit. At least the equations kind of work out similarly. So a photon in that way, the fact that nothing can catch up to it, it's kind of like if you were that photon. I think it's fair to say that it's kind of a little bit like falling through a black hole.
Yeah, definitely, right? Like in terms of rich, well, so like what people often like when people teach special relativity, like imagine someone like flying by in a rocket ship. One of the main predictions of special relativity is that the faster that person is flying by in a rocket ship, if you were to look at them with binoculars, you would see them slowing down, like literally the passage of time for them relative to yours slows down. Um, and the speed of light is that point at which that person's motion would be slowed down so much that you wouldn't see them move ever. So they would experience like, the whole journey, like the whole evolution of the universe would occur to them in an instant amount of time. You wouldn't have time to experience anything. And that's a similar thing happens when someone falls into a black hole. You do see time slowing down for them as their, uh, you know, sense of time is slowed down by the gravitational distortion. If you've seen the movie Interstellar, it's like the same idea. So yeah, the photon experiences all of eternity in zero amount of time. And so it's just flying to the universe, basically just experiences it as a pancake.
I guess like one question I have about that is if it experiences all of time, but then it like gets absorbed by an electron, like what does that mean? Like it just
It's like like
It just
just no
ends.
time.
I
Just
mean, maybe
ends.
it's more okay. So there's like another particle, like so something moving at the speed of light is very difficult to like think about because it's like so far detached from our everyday experience.
Hmm.
But there's a particle called a neutrino, which is like it's like so light that it's almost always traveling at close to the speed of light.
Very close.
So that's like kind of a more like human kind of thing you can think about, where if you actually looked at a neutrino and if that was a person, it would always be moving so fast that it would just be like, moving in super slow motion.
It'll take forever for it to move. It's almost like probably like stop motion, not even slow motion.
Yeah. So
But what
maybe
do you mean?
the neutrino experiences the whole universe in like a second. Well, like a photon experiences it in 0 time, and that's very difficult to imagine. We can imagine like a neutrino as kind of like, bringing the mass down and seeing where it goes.
So wait, so like, would you say a neutrino is more unstoppable than a photon?
Mm, it depends on what you mean. I would say no, because neutrinos, even though its mass is really light, it still could potentially get trapped. Like a really
Uh-huh.
massive star or something, like you could trap certain neutrinos. And in fact, we have detected neutrinos on Earth. You know,
Hmm.
with different types of telescope, like ice cube, for example. It just hunks and hunks, giant hunks of ice on the, is it the South Pole or the North Pole? I forgot. Maybe it's the North Pole.
One of
Yeah,
the poles.
one of the poles.
You're
I
fifty
think I think
percent
I think
I think
North.
it's
chance.
the south. I think it's the south.
Is it the South? Oh, the North Pole
I
doesn't
think
have.
so.
Maybe, yeah. But anyway, basically, with that, with enough material, the neutrinos hit the Earth, go to the atmosphere. Most of them just pass through the Earth. But sometimes, especially some of the more energetic one, could just hit some water molecules and all that, and just like splatter and just cause a lot of disruption. So
Mhm.
neutrinos, they do. We could stop them, and we have stopped them before. So they're not totally unstoppable.
Different though, because you can give neutrinos names. You can say like that one's Fred and that one's Bill, and you can keep track of it, right? Because they have a mass, so they have some. It's not like this like droplet of water hitting into the ocean, and now you can't keep track of it.
Right. Yeah. I mean, I guess keeping track is a bit. Hmm. It's like a
Yeah,
loosely.
should that matter when you're talking about unstoppability that you can name it? That really brings the dark matter versus graviton debate in a
I
different
mean, it's
direction.
not absolute, right? Neutrino is a type of matter particle, and we described before. It's a type of what we call fermion, and it means that it's harder to stack them on top of each other. Although you could, but it's just a little harder. So that means that
It's
it's
easier to distinguish. It's easier to distinguish them apart.
yeah. So there's a clearer distinction. You can more easily and clearly name them. But still, they're still born from the
Mhm.
same quantum field, and ultimately, all neutrinos are basically one and the same. They're not necessarily
Mm.
distinct. But practically, they're a little bit easier to name, I guess, in that way.
They have a certain sense of independence that
Yeah.
bosons just don't have.
Uh, I guess okay, so coming back to the original question that we asked, what's the most unstoppable particle? If it's not the photon and it's not neutrino, and like what would it be? Is my question. Tim, you look anticipatory
So
with
so I
excitement.
would I would say two. I mean, we thought about this. We really did. We really did thought about this. I think there are a few criterions. First, probably it should move at the speed of light, because things that move at the speed of light. I mean, we can argue about this a little bit later. Like things that move at the speed of light truly move at the speed of light. They cannot be slowed down. So that's pretty unstoppable, right? And
But
also,
they can,
huh?
so it depends on whether you count that.
Well, okay, but so if you limit yourself to moving at the speed of light, then we have a few limited candidates. And at the same time,
Okay.
it needs to be that you can't just consume them that readily. I mean, it's not quite stopping them. Like the particle of light is a pretty good candidate, but yeah, most ordinary matter will be able to absorb them and pretty much stop them, right? Like a mirror, bouncing around. So now, with that in mind, there's pretty much only one candidate, and that is the graviton. It's like the equivalent of particle of light, but it's a particle of gravity, and that I
Mm.
think satisfied those criteria, and I think it has earned the spot as the most unstoppable particle. I don't know. What do you
Hang,
think, Mikey?
hang on a sec. Wait. I want to challenge that. Hold on a sec. Like, so everything that has mass, I remember from high school physics, has gravity. And so wouldn't like wouldn't it interact with everything? And so versus like
Yes.
photons only interact with things that are charged, from what I
That was my
remember.
complaint as well.
Wait, did you agree with me, Mikey? Are we banding up against him on this
Oh,
one?
yeah, I had this conversation with Tim right before. right before you got on. But I mean, I think okay, him talking about propagating gravitons.
Okay. Yeah, Tim,
Uh,
what's your rebuttal to this
Yeah,
this question?
so there's a bit of a distinction between a graviton or the gravitational field that, I mean, although this is a distinction that we didn't make so clear in previous episode.
it's
Um,
a very subtle distinction,
it,
especially when you're
it
talking about massive particles.
yeah, it's a very subtle distinction. It's almost like comparing a droplet of water to a bucket of water. I mean, clearly the gravitational force and the gravitational particle, the graviton, it's all born of the same thing, the gravitational field, and or just space time itself, right? So it's an artificial distinction to separate the two, but nonetheless,
Mm-hmm.
we still do in particle physics. So the
Mm-hmm.
gravitational force that we feel, more or less, like the fact that we are attracted to the Earth, it's from a gravitational field. There's not enough jiggling, basically. It's a static gravitational field. We just constantly feel it. You don't feel it undulating, like up and down, squeezing and contracting. You don't feel that, right? So it's
Mm-hmm.
not quite the gravitational particle,
Mm-hmm.
graviton. So if we limit ourselves to that discussion, then yeah. So even though you feel kind of the gravity of the Earth, you're not gonna quite feel that way when you have a graviton traveling by. So, and you're not gonna be able to just absorb it very much.
Is this distinction so this is reminding me of electromagnetism where like if you have an electron or a proton or some kind of charged particle and it's just just there sitting not moving, it's emanating this like electric field, but if you like actually accelerate and it's like moving and jiggling around, it will actually radiate out photons. Is that sort of like the analogy in this case,
You
or
know,
is
the
it
thing, it's
different?
exactly like what we're saying with photons. You can't name them because there's really like the bucket of water. You can
Hmm.
smash the bucket of water and a drop can come out and you can say, oh, that's a photon.
uh,
But the graviton is even more like that. It's like 1,000 times even more like that. Um,
what what do you mean a thousand
Definitely
times more
cannot
like that?
name gravitons. So those are the hardest particles to name.
Yeah,
What makes them hard? Wait, what? I'm confused.
yeah,
Aren't they all over the place?
they are in that way. Yeah.
But the thing is, like what Tim was saying, like this, like if you have just a static electric field, right? We wouldn't
Hmm.
say that there are photons shooting back and forth. That's more like the ocean, right? There's like this ocean around us, and the ocean is a better description than like like a particle. Much like
Hmm.
the way like if you're like you shouldn't describe the ocean as like a billion droplets, right? Like that'll be a very difficult way to describe the ocean. Um, but if you can
So,
actually excite it enough to create a photon, as you were saying, then
mhm,
you can give it a name for at least a few seconds or something. But to do that with a graviton, to actually like push a graviton out of the soup so you can
mhm.
give it a name, that's yeah, we'll never do that.
W- Wait, hang on a second. I want to understand this a bit better. I mean, I understand the practicality of not like describing an ocean with the droplets, but from my understanding, it's made up of droplets. So what, like,
Yeah.
yeah, you might not be able to like pull one out, but isn't the gravitational field made up of gravitons?
Yeah,
Like,
yeah.
a,
Yeah, you
But
can
like
think of it that
super
way. Yeah.
ghostly ones that you can't name.
super what? Super
Super
what ones?
ghostly ones that you can't name.
What does that mean? Ghostly ones that you can't name. Actually, what is the thing of naming it? Like, why is that so
Yeah,
special? I'm just trying to understand that.
I think the key thing is propagating. Whether a particle can move from point A to point B and do something.
Mhm.
Like the static gravitational field and electric field, they can't do that. I mean, they cause objects to move, but they don't have this notion that something travels from point A to B. In order for that to happen, you gotta have these undulating disturbances, that goes up and down like a particle of light, and that's the particle physics distinction. That's the difference between a particle and a static field. I mean, of course, you're right to object that. Oh, that seems to be such a. It's I don't know. It's just an artificial distinction, and that's true. That's true. It's just a
Mhm.
way we describe the universe. That
Well, I mean, actually, like, can I think about it this way though, Tim? Like, I'm only not so sure this is thinking out loud here, but like, right? If you have a massless particle, then the energy of that particle is determined by its wavelength, right?
Yeah, it
And if you
is.
stretch out its wavelength to be like so large that it basically has zero energy, can you really say that it exists? Its energy can be so low that it's like
Yeah.
basically like stretch it out of existence if you wanted to.
Yeah, I mean, so that's the thing about massless particles because you can continuously stretch, uh, you can continuously stretch out the wavelength of a particle to the extent that its energy keeps going down and down and down, and eventually becomes like a static gravitational or electric field. That's why this becomes even murkier because there's a continuous deformation from one to the other, right?
Very
Is
stupid.
Yeah. When you say continuous deformation, are you talking about like imagine I had like a wave-like structure and I were just stretch that out
Yeah,
continuously and it becomes
exactly.
flat. So I can
Massive particles, it's either like it's kind of like an all or nothing thing.
Mhm.
Like you get enough energy to create it, it's stable for whatever reason, and that's the energy, and it's like a hard step from
Yep.
not existing to existing. With
Mhm.
photons, it's you can continuously, you know, existence is very continuous for
Yep. Yep.
photons
Yeah.
Mm. So
or any
you
massive
can't
particle.
so you can't do this with like let's say an electron. You can't like stretch out an
Nope.
electron until it's
Nope.
like flat.
There's a
Nope.
bare minimum you cannot go below, right? And that's the
Mhm.
mass of the electron. That's the bare
It's like a
minimum.
step
Yep.
versus like a hill.
Oh, very interesting. Really interesting. So for things like photons and gravitons, you can stretch them out until like they're basically nothing in some
Yeah.
Mhm.
Yeah.
sense.
That's why
And that's
naming
what
them is
this
kind of weird. If you have a step, you can say, okay, when it goes up the step, I'm going to call that Fred. But if it's
Mhm.
like, like a hill, and it's like, oh, okay, I can kind of name it if it's at the top of the hill. I can call it like,
Yeah.
Thomas or something. But then at what point does it stop being Thomas? It's not really clear.
Yeah. It's not really clear.
Mm, okay, okay. One question that one of the listeners asked me in preparation for this episode is that is the graviton an actual particle? Like the gravity waves have been discovered, but are we so sure that a graviton actually exists?
Pretty darn sure, I would say. I mean, it's
I mean, in a sense, it's like almost by definition, right?
yeah. I would say it's almost as legitimate of a particle as the particle of light, right? We've
Mhm.
detected gravitational wave, and you can think of that as a massive surge of gravitons, all have the similar frequency passing through Earth, and
Mhm.
we observe a handful of them. So we did
Mhm.
stop quite a handful, and we saw this undulation of a massive gravitational wave detector that I think it jiggled it by the width of a few human hairs or something over a few kilometers, which is incredible.
Mhm.
And we discover black holes merger from that discovery. So I would say the fact that we saw undulating gravitational field is pretty much proof for the graviton, I would say.
I mean,
Mm.
see what the person means though is like, could you ever give a graviton a name? Like, could you ever excite one and give it so much energy? Like, could you ever prove that you can do that?
I mean,
Mhm.
I guess
theoretically,
that's a pretty tall
yeah,
order.
yeah,
I guess what
theoretically. hmm
oh go ahead, Tim.
I mean, I would say theoretically maybe possible, but this is the
I'll
problem
never do
that,
it.
yeah, this is the problem that makes it so unstoppable because the interaction is so small that individual graviton will probably never detect. They have to come in enormous tsunamis, like gravitational tsunamis, right? That's what we detected.
Mm.
In order for us to have even a tiny chance to absorb a few of them and then like claim a discovery. And that's what makes it so unstoppable. It's just really hard to track down these guys and stop them in their tracks.
Hmm. Could you also make that argument for like the static electric field with these photons that have been like stretched out so much that they're basically almost non-existent?
I think the difference is that like since we're beings of electromagnetism, we can
Uh-huh.
like take a hammer and just smash the field, and photons will just fly out.
Yep.
But you can't do that with the gravitational field. We don't know any kind of
Mhm.
hammer that can
Well,
smash these
well,
gravitons. Apparently, if we had a collider the size of the solar system, we could, like, that's what it would take to smash them.
Let's clarify a little bit. I mean, you could make gravitons quite easily. Like, just us moving around, we're making gravitons. But those have so little energy. They're so basically so stretched out. They might as well not exist. So it's not fair to say that they're real particles, right? Because there's this ambiguity, right? Like, at what level do we say that these gravitons exist, right? You have to have some threshold. You gotta have set some bar. The bar might be low, but like, for us moving around, these are like wimpy gravitons. So probably doesn't satisfy the existence criterion.
I guess one thing I want to understand that we've been talking about is like with the static field, like if I imagine a wave just like stretched out and then you cause a little bit of disturbance and there's a little bit of like a hump in this wave, but it's like mostly flat. Are you referring to like the ability to name a particle in that way as like you have like a larger peak in which it's like definitively separates itself from like the rest of the thing, like a disturbance
exactly.
or okay.
Exactly.
Yeah, no, so like literally like there becomes a certain point when a photon has so low energy, like is this 1,000,000 photons each with like this amount of energy, or is it 1,000,001 with like each one with a slightly less amount of, like it's the distinction becomes completely I think it's literally ambiguous.
I see. So I guess like so we're talking about if we were to generate gravitons, they interact really weakly. Like, is there any reason as to why, speculative or like definitive, like why gravity is so weak?
I mean, that's actually a theoretical puzzle, right?
That's the greatest theoretical puzzle.
Yeah, I mean, so gravity didn't have to be so weak, and normally we would expect gravity to not be that unstoppable. We would expect graviton to behave similarly to the particle of light. You grab any object, their gravitational interaction would just stop it, right? Maybe like Interstellar, if you watch the movie, don't want any spoilers, but imagine if we live in a world where gravity is highly dominant, we would just have communication devices that uses gravitational interactions, right? We'll absorb and emit gravitons all the time, although whether
black holes.
Yeah, it will just be black holes. But yeah, but in that way, pretty much like in this world that we live in, it just so happens that it's so weak, and pretty much the only way to really guarantee a stop for graviton is just black holes. There's basically no other thing, and black hole stops everything, obviously. Like, it's not just graviton.
Literally, the question of why gravity is so weak has been the number one
$1 million question. More than $1 million.
For a long
Money cannot measure.
time.
The gravity.
How many generations of people have lived and died just dedicating themselves to making any amount of progress on this, and there's been none.
Yeah.
So I'm guessing you two are up for it. Yeah, so I wanted to ask a question. I don't know, maybe this is a bit of a more complicated question, but can a graviton escape a black hole, or like how does that work? Like gravitons and black holes.
Yeah. So this is again because okay, so what makes a black hole is because the gravitational field around it. And like we mentioned before, graviton is the excitation of the gravitational field. So it's almost like when a graviton falls in a black hole, it's literally like you have a drop of water dropping into a massive whirlpool of like water in it. So to what extent did the graviton made it? It's a little ambiguous, right? Like, where's the graviton? But of course, if you follow that undulation I think will follow the same behavior, because once it falls to the horizon, the space-time is going to stretch so fast that undulation will never get like deflected out, right? So it cannot escape just like particles of light. But then again, it's more like, it's not really like the graviton fall into the black hole. It's more like it merged with the black hole. It joined it, basically. I think that's a more apt description, yeah.
Yeah. If I were to like, I don't know, this is a weird science fiction experiment. If I could like generate gravitons more easily and I fired enough of them at each other, could I form a black hole? Just only gravitons.
Technically,
Graviton hitting graviton.
I think you could.
Wait, no. If you had enough energy to create a graviton that you can measure, wouldn't that be a black hole?
I think that literally would be a black hole because it just
Oh,
gravitate. Because graviton is just undulation of gravitational field. If those undulations get really large, yeah, you're just gonna make a black hole. They come together.
So you can't really make one, actually.
But we just
And
wouldn't call that
making one, you would have
graviton.
Huh?
We just wouldn't call that graviton, right? It would just call it a black hole. It's another object made out of gravitational field.
So okay, so I also want to reconcile one thing. So in like Einstein's theory of relativity, like gravity is space-time. So what does it mean for like, and the graviton is gravity? So like, what does it mean for the graviton to like be space-time versus any other particle? Like what does that entail? It seems to have a very special place compared to other particles.
Yeah, I mean, once again, it is a bit of an artificial distinction, right? Like, if for example, if we have perfect math knowledge, we don't need to separate space time and their part and their perturbation, undulation, right? It's because our math is a little bit limited, and also it's because physics aims to describe real life phenomenon, right? And in real life phenomenon, we see like discrete units of particles that exist, particles of light and whatnot, and that's probably what happens with gravity as well, and that's why we have this separation. Be like, hey, when we do mathematical calculation, let's look at the bulk of gravity, or think of it as the default, and any extra undulation, we'll call that the graviton, right? So Einstein's theory, you can think of that, you can think of it as the theory of this fixed kind of like background of space-time, right? And then the extra little wiggles, we can separate it out, even though Einstein's theory still applies. We can separate it out, and we can think of them as particles, and of course add quantum physics to it.
Wait, could you make a graviton that's strong enough to name without making a black hole?
I think that will require a theory of quantum gravity, and that just we don't have.
Literally, if I wanted to, like, if I literally wanted to just build a particle collider so strong that it could make gravitons, then that particle collider would also inevitably make black holes, right?
Yeah, I think so. I think you could. Let me see. Could you collide
that work?
particles and they make gravitons? Well, okay. Like,
If you're making gravitons, you're making black holes, right?
yeah, I think that's pretty much it. Like, basically, you make particles. You can interpret the events this way. Let's say particles. Let's say you collide particles and they create gravitons, right? The interpretation is that you make particles. Those particles create black holes. The black holes merge, and they create gravitons, and the black holes might evaporate, creating other particles. So like,
oh, okay, it's like
that's a fair interpretation, you know.
You're making a black hole binary system that.
Right, although these are quantum mechanical microscopic black holes, so they're not really like conventional black holes, but that's a way of viewing it.
Oh man, Scott Thomas would know the answer to this.
Yeah. So I guess like we're almost at time, and I guess one question that I had about this is like, so gravitons, would you say they're unstoppable in the sense that they propagate forward because like they interact so weakly with everything, so they don't even get phased?
Yeah, exactly, and they travel at the speed of light, so it's pretty much hopeless for you to stop a graviton. It'll just pass right through you.
Unless I'm a black hole.
Unless, yeah, but the black hole stops everything, so you can't fault a black hole for being able to stop gravitons.
No, but the question is, can you really call that a graviton? I think if you can't give it a name, you can't really. Yeah.
So
I think that's
are you
fair.
arguing? Are you arguing, Mikey, that we haven't discovered the graviton because we can't name it yet?
I mean, I'm not sure if it's like really. I mean, okay. That's just not.
Well, I mean, there's a bit of a contention, right? Like, we haven't discovered graviton in the same way we have discovered photons, because photons have, like, to call something ton, right? Usually, implied in this word is that there is a particle-like behavior, and usually there's quantum mechanics in it, right? The fact that photons have these discrete, you can kind of label them individual particles because of these quantum mechanical nature. So in that way, yeah, we really have not examined the quantum mechanical nature of gravitational waves, and we probably will never do that in our lifetime because they interact so weakly. But I feel like for all intent and purposes, like, we know that they're there, but we just haven't quite, labeled those particles. We just haven't quite captured them in the detector and be like, look, we got a graviton. Like, we haven't done that.
It's a really weird question. Yeah, I don't know. Maybe I'll save this for the closing arguments. But
All
can't
right,
catch 'em,
you know
I
what?
think.
All right, let's get to the closing arguments then.
I don't know. It's partly because you asked the question, but like I don't know if you can consider the graviton to even be a particle. If I think about it, like we can think of the photon as a particle because it's possible to give enough energy to one in order for it to distinguish itself from the others and kind of separate it out and give it a name. And in some like human theoretical construction, you can do the same thing with the graviton if you ignore the complications that would come from the fact that it would just make a black hole, and then what happens then? I don't know enough, too rusty to be able to work that out. But there are like real barriers to being able to do that, at least in our universe. And so the person who asks whether or not the graviton can be proven to exist, it's almost like not even about proving that exists, but there is like a continuum between a construct, like something that you just like use as like a construct to explain things, and then if it actually interacts enough to be able to give it its own life, then you can say it actually exists. But yeah, the difference, the fine line between existence and non-existence, I don't know. I think the graviton kind of rides that line like a hairpin, like as close as you can get. Crazy.
Yeah, well,
I don't know if it's possible. I don't know if it even exists.
I mean, that's one of the, but that's because one of his characters, right? It is in some way unstoppable. I mean, whether we like that as a real particle, I think that's maybe a separate story. Yeah, we'll probably never find it really confirmed that it exists in the same way we confirm other particles exist for the graviton. But it only stands to infer that if, like, theoretically, if all the particles that are born from field have that property that you can pick one out and study it, it only stands to make sense that we can do the same with graviton. And I think the fact that we detect gravitational waves, even though not gravitons exactly, only strengthen the case that like these fluctuations exist, and they are out in the universe, and these are some of the greatest messenger in the world, right? Because they see everything, they can travel very far, although they're really faint signals. So understanding these objects can really help us. It has already helped us a lot in understanding the cosmos and some of these black hole mergers events, which is super interesting. So,
but I don't know if we can talk about them as individuals.
Probably not. Well, but in some ways they are unstoppable. But I think in that way we have managed to stop a few of them, and that's how we detected black hole mergers. So the human ingenuity is quite remarkable.
But you can never stop one of them. You could only stop a whole group of them.
A small fraction of a whole group, and by chance, only by chance.
Well, you can never just catch one. Like maybe even in principle, it would be impossible to just catch one, and then they travel in groups.
So there is no strength in numbers for gravitons.
I mean, I guess there is only strength in numbers for
There is only strength. Yeah, one doesn't do that much, I guess.
Oh, Mikey, I wanted to ask you something. Put you on the spot. You said a few, like probably several episodes back, that if you ever like could be a graviton or sit on the back of a graviton, ignoring the initial comment that you're made up of particles that can be stopped, that you'd see all the secrets of the universe. Like, what does that mean? Like, yeah. What does that mean?
I mean,
It
it's
sounds
probably
to me like you actually wrote on the back of a graviton, the way you
in a
claimed that.
dream. I mean,
I mean, sorry. Yeah.
I was just
Oh,
gonna
no, go
say. I
ahead.
mean, they are the ultimate messenger, right? Maybe that's what you're referring to.
Yeah, the only thing I can imagine that I could have been referring to is like, you know, I like this idea that maybe like dark matter, like maybe the universe is filled with particles
Mm,
that like they don't interact with anything electromagnetic,
mm,
and so they just pass right through us. But they talk to gravity and we talk to gravity. So if there is this completely disconnected part of reality from us, the only
mm.
way you could communicate with them would be through gravity, just like Interstellar. Implied.
Oh,
So that must have been what I meant. Yeah, the fact that like
okay.
it could possibly let you into this like
Yeah.
whole dark hidden world that could exist like right next to us.
Wow. All
Next
right,
time.
I'm gonna try to learn how to communicate with gravity now.
Wave your hands.
All right then. All right then, everyone. I want to thank you for joining us, and we'll see you all next